Alright, this is AP Physics 1, recorded notes for rotational kinematics. Something to understand about rotational kinematics is it's just like linear kinematics, which was our straight line motion kinematics, except instead of things traveling in a straight line, stuff's going to spin. And it's not just going to spin in a straight line circle path, it's going to spin about itself, so that will make a difference. So, first definition that you need to know is rotational displacement. Rotational displacement has the symbol of theta, and if you consider a disk like a can of soup that's going to roll, and you think about it rotating from point A to point B, that distance is called your angular displacement. It can be measured in revolutions, degrees, or radians. One revolution is 360 degrees, which equals 2 pi radians, which if you work with your unit circle in your pre-calc class, then you already know this. The best measure for rotation of rigid bodies is going to be the radian, so this is going to be where we're going to use that unit. We won't necessarily use that in our calculators though. So the definition of a radian. 1 radian is the angle theta subtended at the center of a circle by an arc length s, equal to the radius of the circle. So the thought is that our theta is equal to s over r. Or another way to say that would be that our angular displacement is equal to our arc length divided by radius. So angular velocity, which is the lowercase omega sign, is the rate of change in angular displacement. So it's going to be radians per second. Remember, anything that's a rate is really just over time. So we will have our change in theta over our change in time, which will equal omega. That will be our angular velocity, which is radians per second. Now, angular velocity can also be given as the frequency of revolutions. So we can use that f value as revolutions per second or revolutions per minute, which is RPMs, which is what y'all are more familiar with. But we can say that our omega is equal to 2 pi f, and then we'll have it as angular, then we'll have that angular frequency that will be in revolutions per second. So if you think about oversized tires, I don't know how many of y'all might have these on your trucks or on your cars, but if you drive a vehicle with oversized tires, how is the speedometer actually affected? So if you sit and think about that for a minute, you'll think about the fact that when you travel in a larger circle, you're actually making you're covering more distance. So when you use oversized tires, they have an impact on your speedometer. Your vehicle is actually covering a greater distance every time your tire goes around because of the larger circumference of the oversized tire. Your speedometer is actually calibrated for the smaller tires which are sold on your vehicle. So your speedometer is reading a less speed and you are moving actually faster because you're covering more distance in the same amount of time as your axle's rotating. So if your tires are 10% larger than the original tires on your truck, you travel 10% more than your truck actually recognizes. This has 2 effects actually. One is on your speed, so your actual speed's 10% more than what your speedometer is reflecting. So if your speedometer is reading 60, you're actually going 66 miles per hour. If it's reading 40, then you're going 44. So that's just a way to think about that. Hopefully you're not going 100 like I have on an example here. But if you are going 100 on your speedometer and you have oversized tires, you're actually traveling 110. So your mileage, though, is 10% more than what your odometer is reflecting as well, because your odometer is actually on your axle reading. And so when your odometer reads 100 miles, you've actually traveled 110 miles. So it might be a benefit for your mileage, but it's actually bad for your speed, according to her speed limits. Angular acceleration. Now, angular acceleration is the rate of change in the angular velocity. So this is going to be radians per second, or radians per second squared. So we'll use for angular acceleration the symbol of an alpha, and that will equal our change in omega over our delta t. So for our angular acceleration, it's radians per second squared. Now, angular acceleration can be found from the change in the frequency as well, so we can say that alpha is 2 pi frequency divided by time, since we know that omega is 2 pi f. So really it's just a substitution of one of the previous formula that I gave you for omega. So let's talk about angular and linear speeds together. So from the definition of angular displacement, we know that S equals theta times r, because we said that theta was the arc length divided by the radius. So we could say that S value, that arc length, is actually our distance traveled, or our displacement. So that's the linear versus the angular displacement. Now, we know that linear velocity is just distance divided by time. So that would be our arc length that we're covering on the circle, that distance, which we could then substitute in theta times our radius divided by time. And so if that's the case, theta divided by t is actually our omega value. So we're showing how we can make angular substitutions into our linear equations. So we can end up with a linear velocity equals our angular velocity multiplied by the radius. So linear speed equals angular speed times radius. Now we can also talk about the same information when we talk about angular and linear acceleration. So from our velocity relationship, we can find that linear velocity equals our angular velocity times radius. We can rearrange that equation. So if that's the case, we can say that acceleration is the change in velocity over change in time. Well, change in velocity would be our omega multiplied by our radius divided by time. And if you remember, omega divided by time was angular acceleration. So we can say that our acceleration, our linear acceleration, is equal to our angular acceleration, which is alpha, multiplied by r, our radius. So this is just ways to substitute linear and into angular and combine them. So angular versus linear parameters. Recall the definition of linear acceleration from kinematics. We said that it was the change in velocity, or Vf minus Vo, over time. Okay? Well, we also know that A is equal to alpha times r now, which would be our angular acceleration times radius. And we know V is equal to omega times r, or our angular speed times our radius. So we could rewrite this to become alpha r equals r times omega f minus r times omega o divided by t. Well, when we do this, we can cancel out the r's, and your angular acceleration is the rate of change of angular velocity. So we could say our alpha is our omega f minus our omega o over t. So trains ride on a pair of tracks, and for straight line motion, both of the tracks are the same length. We don't worry about them, we just talk about them as a unit. But actually, which track is longer for a curve? Is it on the one on the outside or the one on the inside? The outside track actually has to be longer. Just as a circle with a greater radius is, it has a longer circumference. So, moving on, when we talk about center of gravity or center of mass, this is a specific point at the center of an object. Sorry, there was an announcement, so I didn't hear that. You didn't hear that. So the center of mass is the point at the center of an object's weight distribution, where the force of gravity can be considered to act. So it's actually a single point where all of the weight seems to be concentrated. And if that point is not supported, then things like this can happen. So If the center of mass is not supported, the object will topple. So for example, the center of mass is right here. Well, if we go straight down, there's nothing supporting that. So this is going to fall over. Whereas right here, the center of mass has all this extra part of the car that's going to support that. So this is not going to topple over. This one, there's a lot of extra material on this side, and there's some space between this tire and the ground. So this one's going to be able to ride itself. But if we look at this one, there's not any force down here that's going to be able to keep it from toppling, so that's going to topple. And it's because their center of gravity is here. When you think about it, your center of gravity changes. If you're diving and you're wanting to do somersaults, that center of gravity goes to the middle of your body. And then when you take your arms in and out, that center of gravity shifts a little bit. So you have to pay attention to that. When you're standing on top of like high heels, your center of gravity shifts forward some. So those are kind of some things you have to think about when you're thinking about the center of gravity. All right, this wraps up this set. See you in class.